Hello and welcome back to the podcast, everyone. Episode 136 today. Mark, how's it going over there?
Hey, Jenny. Doing great, yeah. Really looking forward to today's topic. It's one of those things that's been simmering in the background of the tech world for a while. But I have a feeling it's about to, really come to a boil.
Ooh, intriguing. Lay it on us. Something about memory? My notes here say, the death of computer memory. Sounds a little dramatic, Mark. Are the robot overlords finally pulling the plug?
Haha. Maybe just a asterisk touch dramatic for effect. No robot overlords, yet. But it points to a genuine, significant shift. We're talking about the memory that lives right inside our computer chips. Specifically SRAM, static RAM. The really fast stuff. It's running into some serious physical roadblocks.
Okay, SRAM. Right, that's the super speedy memory processors use for their caches, correct? The stuff that keeps everything flowing quickly?
Precisely. It's absolutely vital for keeping those hungry CPUs and GPUs fed with data at the speeds they need. For decades, it was kind of a given. Transistors got smaller, good old Moore's Law, and the SRAM cells built from those transistors shrank right along with them. That meant more cache capacity, faster chips, often in the same physical space or even less. But, that smooth scaling is hitting a wall.
Hitting a wall? How? Like, we just can't physically make the transistors any smaller anymore? Is Moore's Law actually, over?
Well, it's more nuanced than that. It's not so much the logic transistors, although they have their own challenges, but specifically the time SRAM cells. The standard SRAM cell, it's usually this little arrangement of 6 transistors, right? A classic design. But as you try to shrink that 6 transistor structure down past certain manufacturing nodes, think below 10 nanometers, getting into the 753 nanometer range, they start getting, let's say, temperamental, less reliable.
Temperamental? In what way? Like they start forgetting things? That sounds problematic for memory.
Exactly. One major issue is something called Vmin collapse. Basically, Vmin is the minimum voltage the memory cell needs to reliably hold its data. It's 1 or 0. As you shrink these transistors, tiny variations between them become much more significant. It gets harder and harder to keep all 6 transistors in the cell stable without needing to pump in more voltage. And higher voltage means higher power consumption, more heat. Things you really don't want.
Ah, okay. So trying to make them smaller actually makes them less stable, potentially forcing them to use more times power just to stay stable? That feels like going backwards.
It's certainly not the direction chip designers want to go. And the other huge headache is just the physical footprint, the bit cell area scaling. That's the fancy term for how much smaller the area of one SRAM bit gets with each new manufacturing process node. It has slowed dramatically, almost stalled in fact. We saw data, for example, from TSMC's 3 nanometer node. The SRAM cell size barely shrank compared to their 5 nanometer node. We're talking tiny numbers here, like maybe 0.021 square micrometers down to 0.0199.
That time's incredibly small, but I take your point. The asterisk improvement is minimal. And if SRAM takes up a significant portion of the chip area already.
Right. And it often does. In high-performance chips, like big server CPUs or top-end graphics cards, the cache memory can easily take up 50% or even more of the total die areas. So if the logic parts, the processing cores, continue shrinking nicely, but the cache portion barely budges, that cache starts utterly dominating the chip size. And bigger chips mean fewer chips you can cut from each expensive silicon wafer, which, you guessed it, drives up manufacturing costs substantially.
Okay, now I see the connection to my wallet potentially feeling a bit lighter next time I upgrade my PC. Because the memory part isn't playing the shrinking game anymore, the overall chips have to get bigger and thus more expensive to produce for the same performance gain, or even just to fit more cache.
That's a major factor. We touched on this before, but some projections are showing potential costs reaching something like $300 per kilobyte for level 1 cache manufactured on future, very advanced nodes. It's becoming a primary bottleneck, impacting performance per dollar and performance per watt.
Yikes! $300 per kilobyte. So what's the industry doing? Just resigning itself to enormous, costly chips?
Oh no, definitely not. Necessity is the mother of invention, right? This pressure is forcing a lot of creative thinking. Broadly, there are a few key directions. One major path is exploring fundamentally different types of memory technology that might eventually replace, or, perhaps more likely initially, supplement SRAM in certain roles.
Okay, new memory types. What are the frontrunners? What's buzzing in the research labs?
Well, two prominent contenders you hear a lot about are MRAM, that's magnetoresistive RAM, and FeRAM, or ferroelectric RAM. MRAM uses magnetic states, think tiny magnets flipping, to store data instead of storing electric charge like SRAM or DRAM. FeRAM uses a special property of certain ferroelectric materials.
And what makes them potentially better than SRAM? Apart from maybe shrinking better.
A key difference is that both MRAM and FeRAM are typically non-volatile.
Non-volatile. Hang on, that means they remember the data even when the power is off, right? Like the flash storage in an SSD or a USB drive?
Exactly. SRAM, as you know, is volatile. Cut the power and poof, everything's gone. MRAM and FeRAM hold on to their state. This offers potential advantages not just in density, they might scale better physically, but also in reducing standby or leakage power, which is a big deal, especially in mobile devices or large data centers.
Non-volatile cache. Huh, that sounds interesting. Instant wake-up times, maybe? But, okay, I sense the but coming. What's the catch?
Haha, you know the drill. Integrating these new materials, magnetic junctions for MRAM, ferroelectric crystals for FeRAM, into the standard, highly refined CMOS silicon manufacturing process is, well, it's complex, really complex. It adds new steps, potential contamination issues, and compatibility challenges.
So it's not just a matter of swapping out the SRAM recipe for an MRAM recipe in the silicon bakery?
Not quite that simple, unfortunately. Plus, there are often performance trade-offs. Compared to SRAM's blistering speed, particularly for writing data, MRAM and FeRAM can sometimes be slower, especially in their write operations. They might also have limitations on endurance, how many times you can write to a cell before it wears out, or require higher currents to program. Getting them to match SRAM's all-around performance, especially for those critical level 1 caches, is still a major research and development effort.
Okay, so maybe not a direct swap out for SRAM across the board just yet. More like potential candidates for specific roles? Maybe supplementing SRAM?
That seems like a very probable path forward. We might see what are called hybrid cache architectures. Imagine using small amounts of the fastest, albeit expensive, SRAM for the absolute most speed-critical caches, like L1. Then, perhaps using denser, more power-efficient MRAM or FeRAM for larger caches further down the hierarchy, like L3 or even a potential L4 cache, where sheer capacity and lower standby power are more important than raw write speed.
That makes intuitive sense. Using the right tool for the right job within the memory system. Okay, so new memory times types are one angle. What about sticking with SRAM, but changing times how times we build the chips?
That's the other huge area of innovation, changing the fundamental chip architecture. And the buzzword here is chiplets.
Ah, yes. Chiplets. I feel like we've talked about these before. It's like building processors with tech Lego bricks, instead of carving everything from one giant silicon block, right?
That's a perfect analogy. Instead of designing and manufacturing one huge, monolithic die, which gets increasingly risky and expensive as chips get bigger, you create smaller, specialized chiplets. Then you connect them together using advanced packaging techniques.
And how does that help with the SRAM problem specifically?
Well, you could have your main compute chiplets manufactured on the absolute latest, most expensive process node for maximum logic performance. But then, you could create a separate cache chiplet, maybe containing a large chunk of L3 cache, using a slightly older, more mature, and cheaper manufacturing process where SRAM density scaling isn't quite as constrained, or where the cost per megabyte is lower. Or, even more interestingly, you can go vertical.
Vertical? Like stacking them? Isn't that what AMD does with their 3D V-cache on some of their processors?
Precisely. AMD's 3D V-cache is a prime example. They stack an extra chiplet composed entirely of SRAM cache directly on top of the main processor chiplet. This allows them to add enormous amounts of L3 cache, hundreds of megabytes, without making the main processor die itself much larger horizontally. It cleverly bypasses the 2D area limitation by building upwards.
That does sound clever. Are there downsides to this chiplet or stacking approach? It sounds almost too good to be true.
There are always trade-offs in engineering, Jenny. Connecting these chiplets together, whether side by side or stacked, requires very sophisticated and costly packaging technologies. Things like silicon interposers or direct copper-to-copper bonding. That adds complexity and cost to the final product. Also, communication times between times chiplets, while getting very fast, isn't quite as instantaneous or energy efficient as communication within times a single piece of silicon. There's always some latency penalty, however small, and designing software and operating systems to efficiently manage these more complex, potentially heterogeneous memory hierarchies is another layer of challenge.
Okay, so we're pushing boundaries in memory materials with things like MRAM, and in chip construction with chiplets and stacking. What about the fundamental building blocks, the transistors themselves? Any breakthroughs there that might help SRAM?
Oh, absolutely. The evolution of the transistor is relentless. We moved from the old flat, planar transistors to FinFETs, where the gate electrode wraps around the silicon channel on 3 sides like a fin, which gave much better control over leakage current and helped scaling continue for several generations. The next big step, which is happening right now at the leading edge, is the move to GAA transistors, which stands for Gate All Around.
Gate All Around. Sounds rather cozy for a transistor.
Chuckles. It kind of describes it well, doesn't it? Instead of the gate controlling the transistor's current carrying channel from 3 sides, in a GAA structure, the gate material completely surrounds the channel. This is often done using stacks of horizontal nanosheets, or sometimes vertical nanowires made of silicon. This gives the gate even better electrostatic control over the channel, which should, in theory, further reduce leakage and improve performance, potentially helping with that SRAM stability and Vmin issue we discussed.
So could these new GAA transistors be the magic fix for SRAM then? Back to the good old days of shrinking?
Well, that's certainly the hope, right? Better control should times mean less leakage, maybe help with that Vmin stability. But it's probably not a silver bullet for SRAM scaling specifically. Some experts, like Geert Hellings from the Research Institute IMEDIC, have pointed out that these nanosheet GAA designs might actually require taller physical cell structures, which could eat into some of the area savings you might gain elsewhere in the layout. So it helps the logic transistors, it might help SRAM times stability times, but the fundamental times density times scaling problem for SRAM? That likely persists. It's a constant battle against physics.
Wow, it really sounds like a convergence of challenges. Fundamental physics limits hitting SRAM, manufacturing complexity ramping up with new materials and structures like GAA and chiplets, and this looming cost factor.
You've nailed it. And we haven't even really dug into the environmental sustainability angle much, which is becoming increasingly important.
That's a really important point, Mark. We're talking about these incredibly complex manufacturing processes, using things like extreme ultraviolet, or EUV, lithography for patterning the tiniest features, intricate plasma etching processes, introducing all sorts of new chemical elements for MRAM or FeRAM. That must be incredibly resource-intensive, right?
It is, immensely so. Modern semiconductor fabs are some of the most complex facilities on Earth. They consume vast amounts of energy. Think powering a small city. And enormous quantities of ultra-pure water. And yes, the processes involve a wide array of chemicals, some of which require careful handling and disposal. There's a constant tension.
So as we push for smaller, faster, more powerful technology, the environmental footprint associated with times making times that tech potentially gets bigger? That seems kind of contradictory, doesn't it?
It can seem that way. More complex chip designs often mean more manufacturing steps, each step potentially consuming energy and resources, and lower yields on these difficult new processes mean more wasted materials. However, it's not all doom and gloom. The industry is very aware of this and is under pressure from governments, investors, and customers to improve. There are significant efforts underway to find more sustainable manufacturing methods, developing greener chemicals with less environmental impact, improving water recycling within the fabs, investing heavily in sourcing renewable energy to power these huge operations. But it's a massive challenge running parallel to all the technical hurdles.
It adds another layer of complexity to this whole picture. And circling back to the cost implications. Mark, let's talk brass tacks. You mentioned costs spiraling. That potential $300 per kilobyte for L1 cache. If these new memory types like MRAM are complex to integrate, and chiplets add packaging costs, and maybe GAA isn't a magic density fix for SRAM. Are we looking at a future where only enthusiasts or large corporations can afford the latest generation of computing power? What does this mean for the average person buying a laptop or phone?
That's a really crucial question, Jenny. And honestly, it's a major concern within the industry and among observers. Initially, adopting MRAM or complex chiplet designs times likely keep costs high, maybe even push them higher for the top-tier stuff. We're kind of seeing that trend already with high-end GPUs and CPUs. If the cost per transistor, especially for the memory components, stops falling as rapidly as it did historically, it could definitely impact affordability and potentially widen the gap between the high-end and the mainstream market.
So the digital divide could get wider, fueled by memory physics?
It's a risk. However, the counter-argument, or perhaps the hope, is that over the longer term, as these new technologies like MRAM, FeRAM, or advanced packaging mature and manufacturing scales up, they could eventually lead to more times-efficient designs overall. Think better density eventually. Maybe significantly lower power consumption in certain applications due to non-volatility or better process control. That could ultimately translate to better value or new capabilities down the line. But there's definitely likely to be a period of, let's call it cost turbulence and adjustment, as the industry navigates this transition.
It really feels like we're standing at a significant fork in the road. The old path of just uniformly shrinking everything isn't quite working anymore, especially for this critical SRAM component, and that's forcing this explosion of innovation on multiple fronts. Exploring entirely new physics for memory, rethinking how we physically construct chips, refining the transistors themselves, all while grappling with cost and environmental impact.
That's a perfect summary, Jenny. It is forcing a paradigm shift. The death isn't literal oblivion for SRAM, of course, but the end of its straightforward, predictable scaling is definitely marking the end of an era and ushering in a much more complex and diverse landscape for how we design computer memory and the chips that rely on it.
So looking ahead over the next, say, 3 to 5 years, what should we, and our listeners, be keeping an eye on? What are the key signposts of this shift?
Definitely watch the continued evolution of chiplet strategies, how AMD iterates on 3DV cache, how Intel implements its tiles with Foveros packaging, and what Apple does with its M-series chips. Keep an ear out for announcements about MRAM or FeRAM finding their way into actual products, even if it starts in niche areas like embedded controllers or perhaps as L4 cache initially. And listen for progress reports from research conferences on the performance and maturity of GAA transistors, and maybe even glimpses of what comes after *GAA, like concepts called forksheet or complementary feats, CFETs, coming out of places like IMEC.
It's a fascinating, multi-dimensional puzzle. You've got the deep physics, the materials science, the manufacturing engineering, the chip architecture, the economics, and the environmental considerations all tangled together.
Couldn't have put it better. It's a set of formidable challenges, no doubt about it. But honestly, it also makes it a really stimulating time for innovation in semiconductor technology. Constraints often breed creativity.
Well, Mark, thanks for decoding the impending doom of computer memory for us. It certainly sounds less like a dead end and much more like a very complicated and maybe slightly more expensive new beginning.
Haha, exactly. Always more problems to solve, always new ideas brewing. That's what keeps things interesting in this field.
It certainly does. All right, that's all the time we have for today's deep dive. A big thank you to Mark and to all of you for tuning in to episode 136. We'll catch you on the next one.
Bye, everyone. Stay curious.